Hello, everyone. My name is Brian. I am the department chair at the college, and today we're talking a little bit about cryptographic hash functions. So, what they are, what they do, what's the point of these things, and how you might encounter these in practice. So, we've seen a lot of different kinds of algorithms in the class. So, we've seen what? The data encryption standard. We've talked about advanced encryption standard. We've seen some exchanges like the Diffie-Hellman key exchange. We've seen RSA encryption. The cryptographic hash function serves a little bit of a different role compared to some of those previous algorithms. So our previous algorithms, when we're looking at plain text versus ciphertext, a lot of what they're trying to do is ensure confidentiality of sharing information between individuals. The hash function is a bit different. We don't care so much about confidentiality, we care more about data integrity. So what we're going to see in this short little section is we typically tend to use hash functions a lot for like handshake procedures. So it might be like I want to store some personal private information about an individual. It makes more sense for a lot of these databases to store things as hashes, and we'll talk about what that means. Because when I go to like log into some website, for example, and I put my password in, I guess I don't really care about getting the database where I'm storing the information doesn't really care about that password, nor do I want them to have my password. So we have to figure out some kind of way for me to authenticate. So how do I utilize the information from my password to gain access to the website? For example, maybe I'm doing like online banking or something. So how do I go through that handshake procedure so that the bank can verify my identity and so that they don't have the information that I don't particularly want to share with them, which is like my password. And if we go back to our banking example, the bank has a vested interest to ensure that I'm actually logging in with the correct credentials, right? Like they don't want somebody to log in with my information or my stolen information and gain access to stuff that they shouldn't have access to. So they have a vested interest in this as well. But a lot of what hash functions care about is about making sure that the information that we're sharing is from the correct individual, and it's less about sending information back and forth. So it might be helpful for us just to define what a cryptographic hash is. And the easiest way to think about a cryptographic hash is in terms of functions, and it's really a one-way function. And it's going to satisfy some particular properties. So we're going to call it H, capital H for our cryptographic hash function, and we know it has the following properties. So if we're thinking about online banking and password share information, passwords could have various sizes. Names could have various sizes, like other things I might want to store in hashed form. Something like a social insurance number would be a consistent size. But you can see that there are some identifying pieces of information, such as like last name, maybe like, I guess driver's license is probably consistent size, but passwords is the big one, right? Passwords can look very different. Like they could be large, they could be small, they could have special characters, not special characters, capital letters, not capital letters. The idea with the hash function is we have to allow the input into that function to be a variable sized block. So yeah, we could develop a hash function that works on consistent block sizes, but in general, we want it to work on a block of variable size. Now, the main difference here is that we can have an input that's a variable size, but the output can actually be a fixed size. The output has to be a fixed size. So now that we have all of the pieces that we want to talk about, we can actually write out an equation that connects all of these pieces together. So capital H, this is our hash function. So capital H here is our hash function. We have capital X, this is our input block. And then this little h is our output block, which is sometimes referred to as the hash. Oh, hugs for Reese. Yeah, Reese needs some hugs right now. He'll be fine. So when we go to operationalize the hash function, capital H, we would like it to be not super strenuous for our machines to handle. So I want this computation, capital H of X, to be relatively easy to do. That is, it's not super strenuous on hardware to do this. Okay, property number 4 is if we're given a hash H, we want it to be infeasible, computationally infeasible, to find an input that would match with that H. So in other words, if I happen to know the hash value, like let's pretend we're working in a password situation, like my password has been hashed and it's stored in a database. If somebody gained access to that hashed password, it wouldn't really make a lot of sense to try to just run through a bunch of input blocks to try to figure out what that output is. That's what number 4 is saying. So even if my hashed password was stolen, it would be really difficult or really challenging to find an input that returns back that particular output. Okay, so like there's just so many possibilities for that input block X that it's going to be impossible for us to cycle through all those possibilities with a strong computer. That's what number 4 is saying. Property 5 is the reverse. So it's saying if I happen to know what an input block was, I want to ensure that I can't find another input block that gives the same output. So I don't want, if I happen to know the input, I guess I could put that through the hash function to get my output. But I want it to make it difficult to find another input that gives me the same output. Because when I'm thinking about like databases and storing information, that hash is going to get stored in a particular spot based on maybe some of the outputs of that hash. And I don't want a collision to happen. So I don't want another input block to land in that same box over here in the database side. Otherwise, we're going to run into some integrity issues. So that's the idea with number 5. And then finally, we want to make this a little bit stronger in property 6. Six just takes us up a little bit of a notch by saying, so 5 is saying, if I know an input, I can't find another input that matches to the output. 6 is a little bit stronger, saying that I can't even, it's going to be hard for me to even find 2 where I find a collision. So in the event that h of x is equal to h of y, we call this a collision, and a collision devalues the integrity of the algorithm. So 5 is kind of like a weak property, and 6 is the strong property that we're really truly looking for. It's just really hard for us to find collisions given 2 input blocks. Just add salt. Yeah, exactly. Salt that hash. I love that computer scientists actually have a sense of humor sometimes. Because who doesn't want a salted hash? So, a couple of little notes here. Property 4 is called the one-way property. So 4 is the one-way property. It's the one that says it's easy to input stuff to get outputs, but it's hard to go in the reverse direction. If I'm given the output, it's really hard for me to go backwards to find the input. So that's the one-way property of our hash function. Number 5 is sometimes known as the weak collision property. And 6 is known as the strong collision property. But in general, you have this idea that even if I fix one of the inputs, and I maybe know what that output is on the other side, it's really hard to find another input that would gain me access to what's happening over on the other side. Or a stronger way to talk about this is, even if I just allow a computer to cycle through a bunch of different inputs, I'm not going to be able to find 2 inputs that give me the same hash output. So that's what we know as the strong collision property. So there's enough space that's happening over on the other side that this one-way function, we don't see any overlaps, I guess, on the database storage side through the outputs. So I want to work through a small example, maybe a couple small examples, and how we might solve problems with collision, just to give you an idea of what this might look like. So we will kind of briefly discuss, I guess, one of the more famous hash functions, which is the SHA function, and I'll be able to give some of that information to you online. I don't want to go through it in any great detail because it's quite complicated, the algorithm itself. So we'll explore maybe a smaller one so you can kind of see how these things might get created, where some of the problems lie in the theory. So let's consider the following algorithm. Yeehaw! Okay, so that's our 3-step process. And I want to work through these 3 steps with a couple of different examples so you can kind of see what this might look like. Of course, this is nowhere near what I would expect a good hash function to look like, but hopefully it'll give you an idea of some of the things that we are looking out for with regards to having some of those properties listed above. Okay, so I'm going to break up the right-hand side into 2 examples, separated by this dashed line. Let's say one of my examples looks like this. It's 0, 1, 0, 1, and then 1, 0, 1, 1. So this is the input block coming into the function. So step 1 says if the input is less than 8 bits, we're going to pad it with zeros. If the input is longer, we're going to break it up in 8-bit chunks and pad the last chunk. We don't need to do either of those things. So this is the correct size. This is 8 bits. We're good to go. We don't need to worry about step 1. So we're going to pass that into step 2. Step 2 says divide each chunk in half and XOR the right half with the left half. So we're going to break this into 2 4-bit blocks and do something like this. We'll go through the XOR procedure. And this is an exclusive OR, so we should get something that looks like this. So that's my output from step number 2. Step 3 says if you have one 4-bit block, this is our hash. So that's it. We have one 4-bit block here, 1, 1, 1, 0. This is going to be our hash H. Okay, and this input up here, this is our input block X. And that's it. We don't have more than one 4-bit block at the exit path here, so we're good to go. Now, what if I had started with something else? So let's say I had started with 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0. So now I have something that is, 12 bits long. So what we're going to do before we even move into step number 2 is we're just going to pad this with some extra zeros. So we're going to go 1, 1, 0, 1. So this is our first 8-bit chunk. And then to our second 4-bit chunk, we're going to just pad it with 4 zeros. Okay, so that completes the step 1 process. So for step 2, it says divide each chunk in half and XOR the right half with the left half. So for our first 8-bit chunk, we'll do something like this, and for our second 8-bit chunk, we'll do something like this. And we will XOR each of these pairs of 4-bit chunks. So again, exclusive OR, so we should get something like what? 0, 1, 0, 0, and 1, 1, 0, 0. So that'll complete the step 2 process. Now, the output that we get from step 2 now has 8 bits. Right, so now I have 8 bits, or I have more than one 4-bit block that's coming out of this step number 2. So step 3 says if we have more than one 4-bit block, start with the first one and XOR with the next until we XOR with the last one. And the final output's going to be the hash that we're looking for. So we're going to start with 0, 1, 0, 0. We're going to XOR it with 1, 1, 0, 0. And that'll give us 1, 0, 0, 0. So this now becomes our output hash from that original input. So this is going to be our input X. Okay, so kind of 2 examples of varying inputs. And they lead us to 2 different outputs. But notice that the outputs are fixed size. So it's satisfying properties 1 and 2 of our hash function. We can start with various input size blocks, right? So we started with an 8-bit and a 12-bit. But the way we've set up the algorithm is that the output always comes out to be 4 bits in this particular example. So we've made sure to satisfy 1 and 2. Right, block of variable size, output is a block of fixed size. H of x is fairly straightforward to compute. This wouldn't really be hard for us to set up via Python, for example. So number 3 is satisfied. Now, where our particular small example is going to run into some issues is it's going to run into some issues, I think, in steps 4 through 6, or properties 4 to 6. So does it have a one-way property? If I know an output, is it computationally infeasible to find an input? I don't think so. I think we could probably find an input that gives some other output. And then 5 and 6, I mean, if I can figure out how to deal with 4, I can probably also figure out how to break 5 and 6. That is, I can probably find 2 inputs that are going to collide and give me the same output. And the issue really lies on the output sizes here. So if I have 4 bits that are coming out as a result of this particular hash function, I only have 16 possibilities, starting at 0, 0, 0, 0, and going up to 1, 1, 1, 1. So there's only 16 possibilities that I could have as outputs. That's just not enough. So a typical hash function is going to have like quadrillions, if not more. Like, it's going to have like so many possible outputs that it's going to be really hard for us to find these kinds of collisions. So maybe let's just jot a couple of things down here that I think are important. So our algorithm certainly satisfies 1 to 3 of the properties of being a hash function. But not that it may fail, it actually does fail. But it fails 4 through 6 quite quickly, I think. And just as a couple examples, let's say I start with this input, which was one of our examples. So we put this through our algorithm and we got a hash value on the other side that was 1110. So I think that was our first example, right? So we started with this particular input, and then we got this particular output. I will leave it to you as the students to show that if we start with 1110, the output that we get from inputting that into our algorithm is also 1110. So in other words, we found a collision. We found an instance where 2 inputs give us the same output, and that would very quickly make this fail properties 4 through 6. Okay, so we call this a collision when the 2 outputs are the same like this. Oh, sorry, 2 inputs provide the same output. So in this particular instance, we've gone through the example where x was equal to 0101, 1011. We got an output hash of 1110. Now, some other user comes along and they're like, I'm going to choose my password to be 1110. And the output of putting that through our algorithm also produces 1110. So it's not a problem necessarily of somebody knowing my password. Like, it's actually a problem of somebody else choosing a different password and landing at the same spot in my database over on the right-hand side. So there's kind of like an overlap of information. So there's a way to deal with that kind of problem, which we'll talk about. It's called linear probing. But you can see how this starts to cause some security problems. So is it that someone has just randomly found a new password that aligns with my hash? Or is it that they actually know my credentials? And the function itself doesn't really know the answer to that question, right? Like, is it that somebody actually stole my password, used it properly, and got that output of 1110? Or did they just choose something else that happened to land on 1110? In either case, it's a problem with the integrity of the algorithm, right? It's the person in store of the hash, right? Maybe the bank, isn't really going to know the difference between these two passwords now, right? Like, so that's a problem from a banking perspective, or from a database storage perspective. Okay, so how does SHA fix something like this? So SHA-256 is what's currently used, I think, as a kind of universal hash function. Which means that the output, instead of having 4-bit output, it actually has 256-bit output. So if we start to do the comparison of what ours had, which was a 4-bit output, with what SHA has 2 to the 256 possible like output values, which is about 1.15 times 10 to the 77, whereas ours only had 2 to the 4, which was 16, right? So SHA has just a much more robust ability to deal with all of the different inputs that it could receive. Now, I'm going to do something kind of interesting. I want to figure out what this number means. Is 10 to the 80. So our number is about 1/1000th of all of the atoms in the observable universe. Atoms on Earth, 10 to the 50. So our number is about 10 to the 27 times larger than the number of atoms on Earth. The number of seconds since the Big Bang is about 4 times 10 to the 17. So our number is bigger than the number of seconds since the Big Bang. That's freaking phenomenal. The number of grains of sand on the Earth is about 10 to the 19, which again, our number dwarfs the number of grains on Earth, the number of grains of sand. So crazy. That's ridiculous to me. So that's what makes the current hash function so robust. There's so many possible outputs that we could get that we're probably not likely to see a collision anytime soon. Right? And that's where our original example fails. It just doesn't have enough outputs for us to do this matching. So it's possible the probability is less than 0 that we could have a collision, but it's not likely to happen. The probability of a collision happening is so outrageous that we're probably going to have more luck winning the lottery 100 times before we see a collision, like realistically. So to get an idea of what linear probing is and how it could be helpful on the backend database side of things, let's look at just a really simple map. This is going to be a map where I take any positive integer, so S is the set of positive integers. Do I want to include 0 here? I don't think that's important. And the output could be basically the output can be any last digit. So we're going to take that positive integer, we're going to mod it, we're going to take it mod 10. So basically whatever that last integer is in the sequence of numbers, we're going to save that, and that's going to be our map. So let's just maybe work through a couple examples, just so we get an idea for what this map does. So all we're really doing is we're taking our input number, which is 7. We're going to take that mod 10. That's congruent to 7. For a number like 23, we take 23 mod 10, which means it's going to be congruent to 3. It's in the same equivalence class as 3. And similarly, 49 would be sent to 9, 58 would be sent to 8. So that's how our function works. It just takes that last digit of the positive integer that we're working with. Now, is this map going to satisfy all of the properties we need it to be a hash function? Well, the answer is no, because it's pretty easy for us to find a collision. So I've picked 168 and 19,567 for some reason. But these are going to collide with some of the previous inputs that we have. So we know that h of 168 should be sent to the number 8, but this is also equal to h of 58, right? So now I have two inputs that have collided and given me the same output. Similarly, with 19,567, that's going to be sent to 7, and that's going to be similar to h of 7. So if I have 1, 2, 3, 4, 5, 6, if I have 6 individuals that I'm trying to save passwords for, and they've given me their 6 passwords, I've noticed that 4 of them, right, 2 pairs of them have similar outputs, but I don't really have the structure to be able to create a brand new function to deal with the storage of these 6 individuals. One thing that we could do is we could use linear probing to assign these passwords in a very specific way. So the idea with linear probing is if a collision happens, we just keep moving forward in the storage table until I find an open spot where I can store that information. So the only thing that we would need to be careful with if we're going to use this method to store information is that when we go to kind of do the handshake procedure, so the input comes in through the hash function, I have the hash that's created, as well as maybe some other authentication piece like the username. So typically we'll take like a username and a hashed password and try to handshake agreement those things to get you to log into a site. So if the information comes through and the information over here doesn't match, then it's just going to cycle to the next thing to see if it's going to find the match. And it just keeps cycling through the next thing, kind of row by row, until we are able to authenticate that handshake. Or it could be the case that we've kind of gone through a bunch of rows and we hit a blank space. If we hit a blank space, then we know that nothing has been validated, and we can return back an error message to the user that's trying to log in. So if we use the same mapping that we want, or that we used in our last example, the xmod 10 mapping, and let's say I wanted to take some information, so I have 7, 23, 49, 58, 163, and 19,567. I'd like to store this information, and we're going to do this in order, so we do want this to be an ordered procedure. How we're going to think about this: normally I wouldn't store the input X value like this. I'd store something else, like a username or something like that. But just for the sake of brevity and making this simple, let's think about the input and the outputs. So the possible outputs that I could get if I use the xmod 10 way of thinking about storage is that I'm basically going to have 10 places where I can store information. So I can store it either at 0, 1, 2, 3, 4. I can store this all the way up to 9. So these are the possible outputs that I can get from this particular mapping. If I was looking at the very first example that we did, the possible outputs would be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, etc. So there's 16 possibilities for that first example. Here, a bit of a different map, 10 possible outputs. And what we're going to do is just kind of go through each one of these inputs one by one, figure out where I would like to store them inside this database. So 7 would go into the hash function in this case. We'll call it a hash function just for the sake of brevity. Goes into the hash function, comes out at 7. So 7 goes in, 7 comes out. Done. 23 goes in, 3 comes out. So 23 gets paired up with the output of 3. 49, again, I don't think is going to cause any issues. 49 goes in, 9 comes out. So we assign 49 to the output of 9. 58 goes in, 8 comes out. So we'll assign 58 to output number 8. 163 goes in, 3 comes out. So here's where we run into our first collision. So 163 mod 10 is equal to 3. We get a collision. So all we're going to do is we're going to go down to like the next spot, and we're going to put 163 down here. So we're going to save it in the next possible open slot inside of our database table over on the right-hand side. And I think something similar will happen for our last one as well. So somebody uses 19567. It goes into our function. The output is 7. Again, we see there's a collision here. And what's going to happen is it's going to keep moving down and seeing if there's an open space in the database to store it. And in our case, there's no open space until it comes back up to 0. So 19, 5, 6, 7. It would start here. The algorithm says, well, we can't do it there. It comes down here, but 58's already taken that spot. It comes down here, 49 has already taken that spot. So the idea is then it kind of cycles back through to the top of the possibilities. So 19, 5, 6, 7 gets placed up here with 0. So that's the idea with linear probing. If we do find a collision inside of the algorithm and we're trying to store data like this, we could just cycle to the next open spot. And then this, I mean, it doesn't come with some added difficulties. So when I have to go to authenticate, there's a little bit of extra work that has to be done in order to authenticate and or ensure that we send back a correct error message to the user that's trying to use the information. But hopefully that gives you kind of an idea of what linear probing might look like using a smaller example. So to kind of finish up the chapter, we'll just talk a little bit more about kind of the handshake procedure. So if I was in charge of information such as passwords or other kind of personal identifying information, I'd probably want to store that as a hash. That's just from a data security and data ethics kind of perspective. There are probably lots of companies that would really love to have that personal private information about you, and I would strongly recommend against giving away that personal information at the pleasure of convenience, let's say, right? So there's a lot of people that, if you can't figure out what the object is that a company's trying to sell you, then they probably are actually just after your information. That's usually the easiest way to think about it. So like, why is Facebook allowing you to utilize their service for free? Well, they would argue that it helps connect you to all of your friends and family and to the greater world. But I mean, the ability for you to use that platform for free comes at the cost, right? So it's convenient to use it, but that convenience comes at the cost of probably giving away some of your personal information, right? And right now, especially in the age of AI, a lot of that personal information is getting put into large language models. So there's a lot of LLMs that are effectively using your data to train themselves. Whether or not you agree with that or not, it's a different kind of discussion, but always be cautious when you are asked to give that kind of information away to other individuals that may not be as ethical as we are in this class. You called Citi to verify something and they asked for the last four... Wait, the last four of your social security number, then your full social security number, and you were like, yeah, no, yeah, exactly. Like, so I actually just went to go renew my mortgage. And in order to do that, my mortgage broker asked me to basically submit a like facial scan to Persona. And I don't know if you've heard about this Persona debacle and everything that's happened with Discord and their age verification procedures. Basically, Discord, like Persona got hacked and like released like 1 million pieces of personal information. And I brought this up to my mortgage broker and I was like, I don't really particularly feel comfortable giving away like a geometric facial scan of my face along with my driver's license to a company that very clearly does not value ethically storing data, right? Like, and two, why am I doing this anyway? Like, I can just meet with you. Like, I can literally sit, and I did. I sat down and I bought him a coffee and talked to him, and I was like, this is how it used to be, and this is how it still should be. Like, I don't need to be sending my information to some random company that I have no oversight with. Who knows where that data's going? It's kind of wild, man. Then you called back and a different person answered, and she gave me that information with no social security number verification. Oh my gosh. So somebody within the organization was trying to get your SSN. That's crazy, man. I would have reported them. That's super sketchy. So I would say think about it from this perspective. For password storage, we'd want to use hash functions. It makes a lot of sense, and a lot of it has to do with preventing malicious intent. So, and I would say a lot of that malicious intent would be on the data storage side. So if I was a network administrator, for example, I might have access to the table that contains the hashed values of the passwords of the people that I'm trying to protect. If that individual was a little bit shady, and the passwords were not stored with hashes, then they would just have access to your password. And they would probably also have access to your username because those things would normally get paired together. So what we're doing by hashing the password is we're kind of ensuring that the admin doesn't have access to both your login information and your password at the same time. So it's really hard for them to get a hold of your particular account. Also, even if they do steal the hash, H, it's really hard to find an input value that would give that hash. So the one-way property here is super helpful. They can't take the hash function and get back to X. And then that kind of collision property is somewhat helpful too. It's not easy for them to find either your password, capital X, or another kind of password, capital Y, that would give them access to little h, which would be the hash. So that's the strength, I would say, of the hash function. It kind of does this really nice work for us in the background, the way that it's set up. So what happens when you log in? So when you log in with a password, the hash function will work on that password. And let's assume that password gets changed into a hash. What's going to happen then is the ID is going to go into we're going to use the login ID to go into the database and kind of scan through the rows. And if the ID and the output, the hash, match up, that will kind of give you the handshake authentication to move forward. If the ID and the hash value do not line up, then we'll probably get an error message that gets sent back to the user saying either the ID or the hash is incorrect, is typically the way that it's phrased. What do you get if you hash the hash function? Well, you can't hash the function itself. You could hash the hash if you want. You can certainly hash the hash. But the hash function itself isn't like a block of information, right? The hash function is like an algorithm that produces a hash for you. So if you want to have kind of just a quick little diagram of like what's going to happen here, as the user, I'm going to maybe come up to the website. The website's going to ask me for some information. So I'm going to give it my ID and I'm going to give it my password. Now, the password is really considered the input block for the hash function that's available on the website that we're working with. So the ID gets sent over to the server, and our password gets sent into the hash function. And remember, as a result, it's going to pop out h of x, or the hashed value of that input block. Over on the database side, the database is probably going to have pairings of ID and these hashes. So it's going to go through with the ID. It's going to kind of try to find that ID in the system. Once it finds that ID, it's going to return back this hashed value. And then there's going to be some kind of verification check here. So there you go. If we use the ID to go through what's stored in the server will also produce that hash for us. The password will probably get hashed along the way. And then the idea is we now have a handshake or a verification check that things look good. Once we're happy with that check, we get a valid login. And if the hash or the ID, something kind of misaligns in that process, then we're going to get returned that error message of, hey, your ID and password don't match up. You better go check on some stuff.